Shuffle 44 on the bottom right is our last shuffle for the day. So we begin with our ordered packet and we perform a repeat LR. So how this works is you just perform an LR shuffle, left, right, and then you perform an quote LR shuffle on each half. Left, right. Same thing here, left, right. And then the stacking is as follows. Pile 1 is stacked on top of pile 3. Pile 2 is stacked on top of pile 4. And then we stack the right pile on top of the left. Okay? So here, pile 1 leaps over pile 2 and lands on pile 3. Pile 2 leaps over pile 3 and lands on top of pile 4. And then we're going to stack the right pile on top of the left. So that is shuffle 40. So what is the new ordering that we get? We get 1, 5, 2, 6, 3, 7, 4, 8. So expressed in Cauchy's two-line notation, we obtain the following. The top row is always 1 through 8. And so the bottom row is 1, 5, 2, 6, 3, 7, 4, 8. Converting this to cycle notation, we obtain the following. 1 goes to 1, so we have a single cycle, also called a one cycle, also called a fixed point. 2 goes to 5, so we have an arrow from 2 to 5. 5 goes to 3, we have an arrow from 5 to 3, and then 3 returns back to 2. So it cycles around, completing a 3 cycle. What happens with 4? 4 goes to 6, so we have an arrow from 4 to 6. 6 goes to 7, an arrow from 6 to 7, and then 7 returns back to 4, completing a second 3 cycle. And finally, 8 goes to 8, which means 8 is a fixed point. Whatever begins in position 8 is returned to position 8 once this shuffle is completed. So we have 2 1 cycles, or in other words, 2 fixed points, and then 2 3 cycles. If we color code the digits, we obtain the following. And recall that positions 1, 4, 6, 7 are color-coded black, and positions 2, 3, 5, 8 are color-coded red. This will enable us to see what has happened with the fundamental structure of the Bessey sequence after a particular shuffle is performed. And in the case of Bessey shuffles, there are only 2 possibilities. Either the Bessey sequence is preserved, which simply means that the cards that originally began in positions 1, 4, 6, 7 are returned to those same positions, even though they may be moved around among themselves among these 4 positions. The same thing for the cards that originally began in positions 2, 3, 5, 8. They just get sent somewhere to the same set of position values. Now that's in contrast to the inversion. An inversion occurs if the cards that originally began in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment, and vice versa. The cards that originally began in positions 2, 3, 5, 8 get moved somewhere to positions 1, 4, 6, 7. And we represent the inversion in the following way. So we see here that black 1 gets sent to black 1. Red 2 goes to red 5, which goes to red 3, which cycles around to red 2. Black 4 goes to black 6, which goes to black 7, which wraps around to black 4. And then red 8 gets sent to itself. So here we can clearly see that each value gets sent to a value of the same color. And so when this happens, we say that the Bessey sequence structure has been preserved. Let's go ahead and illustrate that using one of our Bessey sequences involving the digits 0 and 1. So here we have the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. So performing this shuffle, we should get back to that same sequence form. Okay, so once again, the repeat LR starts as an ordinary LR shuffle. But now we perform, quote, an LR shuffle on each half. Okay, and here, do the same thing, left, right. And then the stacking here is this leapfrog stacking, where 1 gets stacked on top of pile 3, pile 2 gets stacked on top of pile 4, and then here we're stacking the right pile on top of the left. So we should get back to the sequence form 1 0 0 1 0 1 1 0, which we do. Taking a look at the shuffle diagram for shuffle 44, we obtain the following. We see that 1 and 8 are fixed points. They don't go anywhere. And then 2 goes to 5, which goes to 3, which wraps around to 2. So we should have an arrow from 2 to 5, which we do, an arrow from 5 to 3, and then an arrow from 3 up to 2. So that completes that 3 cycle. We also say that the values 2, 3, 5 constitute an orbit. For the second 3 cycle, it's 4, 6, 7. So it should be the case that starting at 4, there is an arrow from 4 to 6, which there is, an arrow from 6 to 7, and then an arrow from 7 back to 4, completing the second 3 cycle. And those 3 values constitute their own orbit. So technically we have 4 orbits. We have an orbit consisting of just 1 element. We have an orbit consisting of just 8, so that's a second orbit. These are just singleton sets. And then we have 2 orbits, each containing 3 elements. First one is the set consisting of 2, 3, 5, and then the other orbit is the set consisting of 4, 7, 6. Now down below we have a couple of notes here. We have indication that shuffle 44 is actually the inverse of shuffle 10, and it's identical to shuffle 14. So let's go ahead and just remind you of what those shuffles were. So here is shuffle 10. Recall that this is an even up jog, and we'll demonstrate it here in a moment. But this shuffle here is the inverse to not only shuffle 14, which we saw earlier in the series, but also shuffle 44, which we have just introduced today. And the way that we can tell that it is indeed the inverse is the shuffle diagrams should be identical with one exception. The arrows should be reversed. And that's the case here. If you look at the shuffle diagram for 44, down here in the bottom right, they're identical except for the direction of the arrows. And this is another pair of inverse shuffles that are far from obvious. Okay, so let's demonstrate that. So if we begin with our ordered packet 1 through 8 and perform these 2 shuffles in either order, it should return the packet back to its original order. Okay, so I'm beginning with the packet 1 through 8 in sequential order. And why don't we go ahead and perform the even up jog first, followed by shuffle 44. But just realize that we could do it in the opposite order. Shuffle 44 first, and then shuffle 10. Okay, it wouldn't matter. We'd get back to this original order. Okay, so as a good review here, what is the even up jog? Well, this is where you jog forward, push forward the even position cards. So that one there is in position 2. That card's in position 4, 6, 8. And then you strip those out, and now we have a left pile and a right pile. For shuffle 10, we're going to stack the right pile on top of the left. Okay, and I can just go ahead and just show you what has happened. It's scrambled the cards a fair amount. That mixing apparently will be reversed back to the packet's original order if we now perform shuffle 44. So what was shuffle 44? It's a repeat LR. So you do an LR, and now you repeat those same actions for the left pile. and perform an LR shuffle on the right pile. And then for shuffle 44, the stacking is pile 1 gets stacked on top of pile 3, pile 2 gets stacked on top of pile 4, and then we stack the right pile on top of the left. Okay? So if these two shuffles, shuffles 10 and 44, are true inverses, we should get back to 1, 2, 3, 4, 5, 6, 7, 8, which we do. We've returned the packet to its original order, which simply means that each of these shuffles undoes the effect of the other shuffle. And boy, would that be hard to detect, that those two shuffles undo each other exactly. But how easy it is to identify once you have the shuffle diagrams drawn. The shuffle diagrams here are identical except for one thing. The arrows are reversed. And so this means that we can perform shuffle 10 as many times as we would like, along with the same number of applications of shuffle 44, and you can mix how you do that. You could do one of them, and then two of the other, and then two of the first, and then one of the other. So as long as you perform shuffle 10 and 44 in the same quantity, you can perform those shuffles as many times as you like, and you will always return the packet to its original order. And boy, there is no one who would be able to perceive that all of those actions would cancel out each other and in the end leave the packet in its original state. Absolutely amazing. Okay, and we also see at the bottom here for shuffle 44 that apparently this shuffle is identical to shuffle 14. So let's go ahead and take a look at shuffle 14. Now, of course, we can see from the diagrams for shuffle 44 and shuffle 14 that these shuffles are identical. The diagrams are the same and the arrows are pointing in the same direction. Also, the cycle notation for each of these permutations is the same. So that means if you perform the Pharaoh out, you'll get the same ordering of the cards as you would performing shuffle 44. And that is easily confirmed by just performing each of these shuffles on an ordered packet of 1 through 8. We can leave that for the viewer to check that. But as long as we haven't made any mistakes here, this shuffle we can clearly see is identical to shuffle 44. And yet, if you think about the Pharaoh shuffle and this repeat LR with judicious stacking, this leapfrog stacking, it's not at all clear that those two shuffles achieve the same new ordering of the packet. And so finally, we are ready for an application of these 4 shuffles. Okay, so let's turn to our application.